Delighted to welcome Sofia Martinez to talk about transfer systems and model structures.
Great, thank you. So the title is pretty self-explanatory. We've been talking about both things up until this point, and at the risk of the talk being a little too basic, I'm going to define things pretty elementary in hopes that you stay with me the entire talk. This is going to be the goal. And if I didn't do that, you can tell me that later, and then I'll get a little bit sad, but that's okay. This is joint work out of last year's AMS MRC. So these were the people in our group. Yeah, Costanza's here. Yeah, the other people are not here sadly, but you know, they live in spirit on the slides. All right, so let's get started. I think every talk should begin with some motivation, because if not, why are we here? But as Mike said, we all drink the Kool-Aid. So, you know, you already believe a lot of the things I'm going to say, but I'm going to say them anyways. So Y-City transfer system, whole semester long, like, you know, focus group on this stuff. But if you want a slogan, this is the one that I like. So they provide you a kind of nice way to understand programming, analyze the higher comparisons, right? To understand Operads, right? And for the Operads today, in this talk, I want to talk about transfer systems on POSETs specifically, or maybe even more generally, like you can understand transfer systems on categories. And then Y-City model structure. Some of us haven't drinking all the Kool-Aid yet, but like, you know, the people who care about infinity categories and stuff, think you can work model independent, you can. But you know, working with model structures is really useful. They've been useful since they were first defined by Quillen, right? So really they provide a way to compare objects in a category up to some notion of equivalence that isn't as strong as maybe like diffeomorphism or isomorphism, right? So this is the usefulness of it. And obviously a lot of the talks before have shown the usefulness of these. So like, you know, there's a reason to study them. But today I want to talk about how transfer systems actually arise as a particular collection of maps given a model structure and a category. So this is where the two worlds collide. And I'm gonna have a lot of pictures, which are hopefully gonna be the entertaining part of this talk. So let's keep moving. Let me very painfully define a model structure. I should say this is not the definition. This is not the most painful definition, but it is, as most definitions of model structures are, a little bit painful. So you start off with a category, right? And you ask that there are three classes of maps in your category. You call them weak equivalences, cofibrations, and fibrations. And these are some like symbolic notations that I'll use. Mainly you should remember that W is going to end up being like in a shaded region. So all the maps in shaded regions are weak equivalences. And then if you happen to be both a cofibration and a weak equivalence, you'll be in pink, right? So you'll be an acyclic cofibration. And if you happen to be a cofibration and a weak equivalence, you'll be called an acyclic fibration, and you'll show up in purple in all the pictures you'll see today. So you should think of the top thing as pink, even though it looks maybe different to you, or the bottom one purple, which also maybe looks different to you. And you ask that, firstly, W satisfies a 2 out of 3 property. So if a map in W is a composition, looks like a composition, then if 2 of the 3 maps are in W, then the third one must also be in W. And then the second condition is that these two pairs of like collections of maps, so acyclic cofibrations and fibrations, acyclic fibrations and cofibrations, form something called a weak factorization system. There are 2 things that go into this. Mainly, you can factorize with respect to these 2 collections. So I've described this for you here. Any morphism can be decomposed as something in AC followed by something in F, and then either something in C and then followed by something in AF. And then similarly, lifting says you have a square where the left-hand side is something in AC and the right-hand side is something in F, then you can lift. And analogously, if you have something in C on the left and something in AF on the right, again, you can lift. So again, a painful definition, not the most painful definition, but the one, honestly, that I like best. I should remark that this definition is sort of overdetermined in a lot of ways, right? So we've kind of been aware of this. I don't need to tell you the 3 classes of maps. I can tell you 2, and we're good to go. Essentially, based off of these lifting conditions here. And something else to note, which we can't see it here, is that isomorphisms are gonna be morphisms that are in all three classes of these maps. This is something useful to know, as I go on with the talk. Okay, so here's some observations about, this definition. First and foremost, the AFs actually form a transfer system. But what's a transfer system? Oops. Mike kind of told us this morning, this is, you know, the definition again, in some sense. A transfer system in a category is a wide subcategory where you have closure under callbacks along any morphism in the category itself. So let's sort of investigate an example. I want to consider the category where, like, they call it the like subgroup lattice category in some sense, right? So each one of these dots is a subgroup of the cyclic group of order PQ, or PQ or prime, right? So I call this one, which I won't decorate, but this is the trivial group, this is CP, this is CQ, and this is CPQ. And all the morphisms there are the inclusions. And now I want to understand a model structure on it, namely I want to understand the AFs on it, right, the transfer system. And a valid one is the following. So like I said, if it's shaded in red, it's a group equivalence, and if it's purple, it's going to be an acyclic vibration. So this dot being shaded in red just means the only group equivalence here is the identity, right? Similarly here, this whole region being red means not only are the identities with equivalences, but also the map between it. But since it's also in purple, it's also an acyclic vibration. So this is a perfectly good transfer system for you. A little bit basic, but lo and behold, it's an example, right? And again, I'm only going to tell you what like W and AF are for the most part.
So, just to make sure, I'm not gonna, I will describe the model structure of this little category,
Yes.
but not a canonical one. Just-
No, just one. There are many. Right. I'll show you them. Okay, so a few remarks about this though. When you're working on a lattice, it turns out W is what we call decomposable. So it satisfies kind of an even stronger, like 2 out of 3 condition that I've kind of shown you here. But the idea is that in the picture, you'll never have like just a shaded region being this diagonal. It's gonna end up being, if you have this diagonal being over equivalent, you're gonna have this whole square. So that's something to keep in mind. And then the identities, because we're working on posets and whatnot, are gonna be only isomorphisms on these lattices. So that's also something to keep in mind. We're working in a very particular setting. It makes things really nice. Okay, so in general, when we're working with model structures, as we've kind of noticed across the talks, it's like really hard to get more model structures sometimes. One way people have done this historically is they've actually started with 2 model structures and they look for a functor between them, and then they append the word quillen to like all your model or all your like category theory notions, and you say, okay, it's quillen if all the model things like match in some meaningful way. We're not going to do that. That's like too much already. We want to start with the model category, and then on that same category, you get another model on it, right? Like this is kind of a more elementary step, right? If I give you a category with a model structure, how do I get another one? And this is done by right and left localization. I abbreviate it here. Also, not consequently, right is going to be denoted in purple, and left is going to be denoted in this pink. And the idea is you want to increment the number of weak equivalences you have, or you want to increment the collection that is W, right? While fixing other sets of collections of morphisms, if you will. So this is the idea behind right localization. You want to keep the acyclic cofibrations the same, and then with left you want to keep the acyclic fibrations the same. And because of these axioms in the definition I gave when I started, that has the effect of really increasing the other collection of morphisms. So right localization, you're going to have more purple, right? So more AFs are going to show up in the diagram, and when you left localize, you're going to have more pink. So more ACs are going to show up in the diagram. So let's do an example. This is as much as I want to say about right and left localization. I'm aware that there are more technical definitions in terms of functors and so on and so forth. For the sake of the picture, this is all I wanna say. So let's take the model structure we had before and try to localize it a map, which is not a weak equivalence, right? So the point is, again, increasing the collection of weak equivalences. So let's try to understand what it means to localize here, what it means to right and left localize here. So I've done both for you here. So if you try to left localize at this arrow, this is what, you know, the pink arrow labeled L means left localizing at what's meant to be the same color, like here and here, right? Anyways, so I move across this pink arrow. I want to make this map, you know, and we say weak equivalence. It also turns out it's going to be an acyclic cofibration by these like decomposition axioms that I stated in the original definition. So it turns out this arrow is going to end up being pink, and then you can kind of deduce that the other arrows in your diagram need to be acyclic cofibrations as well, while this stays an acyclic fibration, because then you're moving along a left localization, right? So the acyclic fibrations better stay the same. And then sort of analogously on this side, when I tried to right localize here, I'm consequently trying to increase the like red shaded region, right? And I'm trying to increase the amount of purple arrows that I have, right? Acyclic fibrations, whilst not affecting the acyclic cofibration. So this is the resulting model structure. If you tried to localize at some other arrow, let's say this one, it's meant to be in blue, you can sort of investigate what happens when you left and right localize at those at that arrow, and it turns out you get pretty different model structures, right? So this arrow here turns out to be an acyclic cofibration, whilst here when you right localize, it'll be an acyclic fibration. So this is sort of the example I want to do, and the point I want to emphasize is that when you move along this again, what is meant to be a pink arrow, there's going to be more acyclic cofibration showing up in your diagram, and when you move along this right localization arrow, there's going to be more purple arrow showing up in your diagram. Okay. So this is how you can get more model structures given a model structure, right? It turned out there's this really fantastic theorem, author present. So if you have questions about this theorem, and Helen is one to talk to. I guess because Sam is also here, and I guess Scott's also here. So a lot of only one author is not present, actually, so you can really flag them down and get other perspectives on this. They have this really great theorem that says every model structure on a total order lattice can be obtained via a sequence of right and left localizations. So let me start at the trivial model structure, where I've told you what the trivial model structure is here. So the only weak equivalences are the identities themselves, and then all other maps are cofibrations and vibrations. So they're saying that if I try to, you know, right and left localize anywhere on such a diagram, it's pretty like simple lattice, I can get to all the other model structures. And this sort of motivated our group to try to understand what it means to right localize for things that don't look like the total order lattice. And we described well the process. And it turns out we can, still taking a lot of work. But we can, and this is sort of how our theorem goes. So given a model structure where, you know, you tell me what the W is, you tell me what the AF is, on a lattice, we can describe for you a morphism set, so a collection of morphisms, right, which induces a model structure exactly coinciding with right localization. So we have an honest to goodness description, a recipe, algorithm, if you will, for localizing at what we call a short arrow. And that's what this, like, you know, this is the right localization arrow that I was denoting earlier, and this is our description, which again, like, I can talk more about it later if people are interested, but it's involved. Oh, so the question is it true more generally? And I'm here to tell you, well, kind of. So if you you try to understand this theorem for the case where you're considering the subgroup lattice of CPQ, we can do this. So let me show you. So let's say you start with the trivial model structure. I have it for you there, and I've labeled it in different colors what maps we can localize at. And let's exhaust options. So the first level here, I've kind of shown you what happens when you right localize at that green arrow. No way. At this green arrow, you'll write it something like this. What happens when you left localize at the blue arrow, right? This one, you'll write it something like this, and so on and so forth. The black arrow is meant to be the top one, and the brown arrow is meant to be the bottom one. We can go through and do this. And that's all well and good, and then, you know, you exhaust options again, and you write them all down, and it's good. This is a proof, of the talk. This is as good as it gets. But you can do it, and you know, you get this picture, and it's, you know, kind of surprising. I mean, in some sense, surprising that you get, like, everything's connected, right? Like, I can get to everything else. And we'll leave it there for another 30 seconds, so you can, like, convince yourself that, like, wow, like, this is cool. Yeah. Maybe I should say, while you're staring at this, it turns out, like, for example, this arrow, some of these arrows have like 2 nodes at the start of them, and it just means that if I right or left, depending on the color of the arrow, at those 2 vertices, they're going to result in the same thing. That's all I'm saying. So that's what that means. So, for example, this one on the side here, you're trying to right localize at the 2 vertical arrows. You'll write it something like this. Fantastic. So you ask the question again, well, is it more general than this? Like, can we get more general? And the answer is no, sadly. If you consider, you know, just one, you add one more row, right? Like, you consider the subgroup lattice of CP Q squared, right? You just added one row, and you're looking at transfer systems on this thing, or model structure on this thing, really. You realize that there's a counterexample. Well, there's really 2. It's really many. And you stare at these for a while, and you're like, wow, there's a lot of those. And you can, like, sit there and check, like, does this come from, do any of these come from localization, right? This is really the question at hand. Can I find a model structure that doesn't arise from a right or left localization? All of these don't. Trust me, I sat down and checked. Okay, and I'm, like, fairly confident, but these are all of them for this subgroup lattice. But again, if you start this long enough, you can maybe group them. Maybe. This is like the combinatorics of the game, right? Like, maybe you can group them, and maybe you recognize that something weird is going on, right? So let's look at this first group. These 2 I kind of put together because, well, their weak equivalence blocks are like 2 parallel lines, and you can still localize here, but this doesn't result from a localization. Weird, right? So you can localize at any of these vertical arrows and still get a valid model structure. And then also, interestingly enough, put these together, because if you look at these, you might, you know, when you play with this enough, you think, oh, I'm good at this, like, I know what I'm doing. Maybe this is a right localization of something, right? Like, maybe I can break off this object here, and it comes from a right localization, because, you know, right localization didn't add purple edges, right? So you're thinking, oh, maybe something in that group comes from something like this, where you know, the transfer system in here is the one I have there. So, and I'm here to tell you that, well, this isn't actually a model structure. So, you know, as it goes, a lot more questions than answers here. What do we do with this? And what I kind of want to leave you with is that if you stare at this long enough again, you'll realize that these transfer systems are not saturated. We haven't really talked about what it means to be saturated yet. I hope someone will. But the idea is saturation is the idea that these collection, these AFs, right, the things in purple, satisfy a particular 2 out of 3 condition. Namely, if you have something that I like to call half smile, half smile, because half smile's in there. If you have half smile, then you better have full smile. Okay? And that's a lot, there's a lot of that there, although some of them don't look like it, but like, for example, like this and this is half smile. So they're all not saturated, so that's interesting. So now the question is, how is localization playing with the saturation business? We have a few ideas. We kind of have some modified statements of the theorem I stated earlier. Due to a help with Scott, Pyle, and Costanzo, right? Maybe we can arrive to all saturated model structures by means of right and left localization. But it's certainly true, and we have examples that you can certainly right localize at something saturated and arrive at something unsaturated. So something's going on. But like I said, more questions than answers is what I have for you today. Yeah, I'll just give you a few references if you're interested in learning more about this stuff. The papers are there. The Costanza in progress this year. You have a deadline. Yeah, anyways. I think the right place to check this around and learn more is here. This is kind of where I grab the definition of saturated, so you can go there, and of course, maybe people know where to learn about model categories, but alas. I'm just gonna finish by saying thank you, and I'll take questions now.
That's cool.
So on the slide with like all of the model structures on CP2,
Yeah. Let's look at
I
that again.
counted 23 of them.
Yeah.
Which like, I mean, so okay, the power set of like edges there is of size 32, but a bunch of those don't correspond to our transfer systems, or they generate the same transfer system. So by some very fishy pigeonhole principle, this appeared to be more model structures than transfer systems. Like, do you have a sense of like what that means for us? Like, can I think of like the size of like, you know, we have like this operation of taking the acyclic vibrations that takes me from model structures to transfer systems. Like, do you have any sense of like morally what it means when my fiber is of cardinality greater than 1 for a given transfer system?
I'm not sure, yeah.
Okay.
Maybe, yeah, maybe the sound.
I would be interested in.
Yeah.
A transfer system is half a weak factorization system.
Yeah.
And 2 weak factorization systems might or may not form a model structure. So a transfer system is half of something, which is half of
Something.
a possible model structure. So you basically form pairs and then pairs of pairs and cross out a few illegal ones, and that's when you arrive at something like that.
Yeah, I think it is, there's some instinct there where you're like, oh, if I have a model structure, I can get a transfer system, right? I mean, the converse is not true because of everything you just said, right? Like we need the other half, so I'm not sure.
Other questions?
So
Yes,
I pardon my ignorance, does the discussion of transfer system recover transfer systems when you have non-normal subgroups?
We've only looked at abelian so far.
yeah, we're gonna look to the billion, so I'm not sure.
I have another question.
Yeah,
Which is this business about vascular localization.
yeah,
It clearly, has an effect on the underlying transfer system.
yeah,
But does it have something comprehensible from the perspective of algebras over the associated operads?
I'm not sure. Yet. You always keep learning, of course. Yet. I mean, I think, maybe what I'll say is like. Yeah, maybe I'll, it's better, I think.
Should, thanks, Sophia, again.
Yeah.